Namaskara. We were looking at the performance of a data structure under a slightly different model. We were trying to design or look into the amortized cost, which will match the total cost as per the regular one. Okay. So, we are going to look at a new data structure called Splay trees. This is to implement the dictionary ADT. Dictionary ADT works on any totally ordered set. We assume that we are working on set of integers. Okay. Whatever we are working, it can be extended for, or the same logic can be applied for any totally ordered set. We will assume that a set S is set of integers. Okay, and you can do insert x s, delete x s, and search x s. These are the three operations you can do on S, and in order to carry out these operations, how would you represent S? Okay. What data structure will you use to store the items of the S? In order to get all of them done in log n time, order log n time, we know that balanced binary search tree, red black trees, these are all the data structures that can be used to store the data, that is store the elements of S. And if you use either balanced binary search tree, this is also known as AVL trees or red black trees, then you can carry out all these operations in order log n time. The code for them are fairly complex. The proof of correctness and argument that you have a log n bound, etc., are also mathematically subtle. Okay. And now we are going to, but each operation takes only order log n time. All these operations you finish in order log n time. So, a sequence of n operations on dictionary O1, O2, On, this is going to take order n log n time. Any sequence of n operations will take order n log n time. That is because we have a guarantee that each of them is going to take order log n. Now we are going to remove the condition that I don't want to have the bound log n, but I want to still have any sequence of n operations should take n log n time. Okay. So some of the operations may cost more, obviously correspondingly some of them should cost less, and they will balance out, and the total will still be n log n. Therefore, as far as the worst case performance is concerned with, the same bound works. Okay. However, our data structure design becomes lot simpler, implementation detail becomes lot simpler. That is because we do not have to have the bound of log n for every operation. Okay. How this relaxation helps, we will see that in the design and analysis of our new data structure, and this is called Splay trees. So, Splay trees are basically search tree, it is a binary search tree. What is a Splay tree? It is basically a binary search tree. It is a binary tree. So, each suppose you have A, B, C, okay, the value B is less than A, the value C will be greater than A, assuming all the elements are distinct. Okay, we are not going to encounter the equality case. For every node, the value on the left is smaller and the value on the right is larger. Well, this should not be true even locally, it should be true globally. In other words, value on the left subtree Okay. Value on the subtree, all these will be less than A. The values on the right subtree, all these values will be greater than A. Okay. Every value on the right will be greater, every value on the left will be smaller than the value at a node. This should be true for every node. Okay. So when this is true for every node, then a tree with the values like this is called binary search tree. It is a binary tree and it is a search tree. And the complexity of searching for an element, it goes more like our binary search. You start from the root. For example, if A is the root, if the value you are looking for is smaller than A, you go to the left, and if it is larger, go to the right. So you keep going from a node either to the left or right and reach the next level. So in this way you may keep going down and down, and the worst case complexity is proportional to the height of the tree, the length of the longest path from root to a leaf, because you may take that root and finally you may conclude it is there in the set, or you may conclude that it is not in the set after taking that long path. Okay. Therefore, the complexity of the search, insert, delete, all of them will be proportional to the height of the tree. Okay. So what the red black trees and balanced binary trees were doing is they were trying to get the control on the height. They will make sure that after every operation the height of the tree is always log n. So whenever you perform an operation on the data structure, the cost is not going to be more than log n. So immediately you will do the structural adjustment. For example, immediately after insert, if there is too much of skew in some direction, you rotate it and then you do something and make sure that the height gets controlled. That is because your goal is to make every operation upper bound by log n. You immediately do the repairing act and get the control on the height. Okay. So that is what was done. So in any binary search tree, the cost of the operation, okay, in any binary search tree, cost of dictionary operations is bound by height of the tree. Because you have to start from the root, keep going to the left or right, and your process may go all the way up to the last level, and therefore it is proportional to the height. Okay. And now we are going to design a data structure in which the operations, some of the operations can take more time, but we are going to prove that any sequence of n operations, okay, any sequence of n operations are going to take only time order log n, n log n. Okay. So let us see how that works. The key operation that we are going to do is called the splay operation. Splay at a node x. Splay at a node x. So this operation will be triggered from a node x. We will see from which node this gets triggered later, but suppose you trigger the splay operation at a node, what will happen after that? If x is the root, do nothing, just halt, that is all. If x is a root, do nothing, splay x, is triggered when x is at the root, it will not do anything, you are going to simply halt. If x has a parent but no grandparent, that means it is like this: x has a parent, let us say y, but it has no grandparent, that means y is the root. Y has no parent. Only node in the tree which does not have a parent is the root. All other nodes have a parent. So it is like this. Okay? X may have other in the tree. So whatever we have, we call them arbitrary, let us say A, B, C. A, B, C are trees, binary search trees, okay, arbitrary structure. We do not have to worry about them, whatever is there, let it be there, okay, but call them, refer those substructures as A, B, C. So if x is root halt, if x has, this is the case 2, this is case 1, case 2 is like this. It may be like this, or there may be a left right symmetric situation where it is like this. Okay. We will consider only one of the cases. The symmetric cases are handled by physically exchanging left with right and right with left. You will get the code for the left right symmetric cases. So we will discuss only one case. So the case 2 is that x has a parent but no grandparent. Therefore it is the root, y is the parent of x is the root, and in this case what we do is the following: we move x up. That is what Splay will do. Splay will attempt to move x to the root actually. For the x to go to the root, if you do one rotation, that is good enough. So the rotation that we have to do here is called the right rotation. Right rotation will promote x, which is to the left of the parent, to the position of the parent. Therefore, the following transformation will define the right rotation. Okay, y x a b c. Now x will take the place of y. Since x is to the left of y, the value of x will be smaller than value of y. So value of y is larger, therefore y should go to the right of x. X already has to the left a, x has b on the right. X earlier had b on the right. Where will you accommodate that structure? Because y has taken the position on the right. Now you see that earlier x was to the left of y. Now the left position is vacant because x has taken the position of the parent of y. Therefore, to the left of y you associate b, let the right of y be intact c. Okay? Therefore, the right of x must be changed, the left of y must be changed, and x takes the position of y. When you do all these steps, you would have done a rotation. This is called right rotation. You are turning this way, so it is a right rotation. In a right rotation, left child will be promoted up. X is the left child of y, it is promoted up, and then it has taken the place of y. But y is the root. since y is the root, x has become a root now, it is going to halt. So after this, halt. So what is case 2? Perform one right rotation and halt. Because when you do one right rotation, x takes the place of the parent, but parent is the root. Therefore, x has taken the place of the root, which means x has reached the root. It need not go any further up. Therefore, you can halt. Okay? So, the actual cost is order 1. The actual cost is order 1. For the case 1, you do nothing. That is also order 1. Here, one rotation. Rotation involves changing some pointers, and then you will have this reconfigured tree by just changing these pointers in this way as shown in the picture. Okay, you would have achieved the right rotation, and one right rotation and halt. But suppose x has got parent and grandparent, so somewhere down in the tree, that is case 3. Okay, in case 3 we do that, we do the following. Case 3, x has y as parent and z as grandparent. X has y as parent and z. So there are two possibilities here. Okay, one possibility is x is like this, y is like this, and z is like this. Z is not the root. Z may or may not be a root, but it is somewhere down in the tree. X is a node which is somewhere down in the tree. It has a parent and grandparent. Now let A be the structure here, and C be the structure here, and D be the structure here. Okay? So if this is the case, you reconfigure it in the following way. Okay, you promote x 2 levels, and x should take the place of z, and y is larger than x, z is larger than y, because y is to the left, y is smaller, that means z is larger. So you are going to have the following structure: x, y is larger than z, y is larger than x, z is larger than y, and it will have A, and then this will have B, and this will have C and D. It will have C and D. This is achieved by what is known as double rotation. First right rotate at z, then right rotate at y. When you right rotate at z, y will be promoted. Again when you right rotate at y, right, x will be promoted. So in 2 stages, but all of them are order 1. You do not have to do 2 rotation, you can directly do this pointer changes to configure like this. For example, left child of x is A, so do not touch that. Right child of x, earlier it was B, now it is y. And parent of B was x earlier, now parent of B will be y, because you want to attach that to y. Earlier left child of y was x, now the left child of y is B. So in this way, by changing these 6 pointers, you can reconfigure this structure to this structure. So this can be achieved in the following manner as well. Okay, right rotate at z, right rotate at Z followed by right rotate at Y. When you right rotate at Z, what happens? This configuration becomes Y, Z becomes the right child, okay, Z become the right child. So Z will have D, the right child of Y, which is C, that will become left child of Z, and left child of Y is intact. This is X and that has got A, this is intact. So this is right rotation at Z, okay. Now right rotate at Y, move Y again. So X goes up, Y comes down, okay. The left child of X is same, but the right child of X becomes the left child of Y. The right child of Y is intact. This is Z, CD. So you see that the final configuration is obtained. Therefore, right rotate at Z and right rotate at Y achieves this transformation. So if you have written the program for right rotation, that is good enough to handle all the cases. Right rotate twice, you get this, okay. This is case 1, all right. Now there is another case where you have Z, Y, earlier X was to the left, now X can be on the right. So this may be A, B, C, D, all right. It might be like this, the logic is same, right rotate at Y and right rotate at Z. Here first you right rotate at Y so that Y becomes the left child of X, okay. Sorry, here not right rotate because it is to the right, you have to do the left rotation. Left rotation means right child will be promoted. So left rotate at Y, that will transfer this to Z, it will have X, Y will fall down to the left of it, the left of A will be like this, the X D will be there as such. This is left rotation at Y. Now right rotate at Z, right rotate at Z, it will promote X, it will have Z to the right, Y to the left, Y will have A and B, Z will have C and D. This is the final configuration, left rotate and right rotate. Left rotate at Y, right rotate at Z, you can see that X has been promoted to the place of Z. It has moved up 2 levels. It has moved up 2 levels. So do this and recursively splay at X. So splay at X in this case recursively proceeds at the new position of X. Therefore, until X goes to the root, it will keep moving up 2 levels, right. If x starts at an odd number of level, suppose the splay started at, let us say, at level 11, what happens? The first splay operation brings it to 9. The second one promotes 2 more level, brings it to 7, then 5, then 3, then 1, then case 2, 1 rotation and stop, because that will bring x to the root. It will bring x to the root. If it is at even level, let us say at 8, perform this operation, promote 2 levels, it comes to 6, then 4, then 2, then to level 0, that is, it has come to the root. Halt. So either case 1 or case 2 is used for halting. Case 3 is recursively it will proceed, because it has to keep moving up x until x reaches the root. Therefore, after doing this, recursively continue splay at the new position of x. Now you look into x, look into the parent and grandparent, see how they are relatively located. If it is like this, do this and recursively proceed. If it is like this, right, if it is like this, do recursively and proceed, and if it is like this, do this and recursively proceed at new x. The idea is you recursively proceed at new position of x until x is moved to the root. So splay x means it will start from the wherever x is, and then the splay operation will be done. So splay operation is going to reconfigure the tree. It is going to move some tree here and there, and then it is going to reconfigure the tree. Finally, x has gone to the root. Okay. So how is the dictionary operation done? So the dictionary operation is done in the following way. Every operation will be followed by a splay operation. Every operation will be followed by a splay operation. Search x. How do you search x? You go to the left, right and other things. Let us say it is there in the tree. Okay. You are searching for x and x is found in the tree somewhere. Start splaying from that x. Suppose x is not there. It would have failed in a particular node, saying that x is not there. Start splaying from that node. Insert x. Do the regular insertion. Start splaying at the node that is inserted. Delete x. After deletion, from the parent node of the node that is deleted, splay. Therefore, every operation will be accompanied with a splay operation. Every operation will reconfigure the tree. The splay operation is going to reconfigure the tree. It is doing in such a way that the height will be automatically controlled by this process. Though some of the splay operation may be expensive, it will render several other splay operation very cheap, and it will average out. Okay. Therefore, we have to see how that magic is happening. All right. So splaying of x, splay x means move x to the root by a series of rotations. So rotations are the basic operations on binary search tree, which preserves the property of binary search tree. A binary search tree after rotation will continue to be a binary search tree, but you might have promoted one element up. Okay. So when you keep on doing rotation, you will keep moving the elements up, and it will finally reach the root. So typically we will try to perform the rotation at its father or the parent to promote x, but notice the way in which we are promoting when it is left, right, z, y, x. We rotate at z and then rotate at y. Alright. This is a very subtle change, and it is the ingenious move by the designer of the data structure. When you do like this, you gain efficiency. If you rotate at y and then at z to promote x, that is promote x to y and then promote x to z's place, that is not giving efficient one. From z pull y first, then at y pull x again is the way it is going to work. Very subtle change, but the authors have found out that that way of reconfiguring is leading to a very efficient solution. Okay. Therefore, we have to find out the amortized cost of Splay operation. What is the actual cost? The actual cost is whatever is the number of splays you have done to move up. That is the actual cost. Okay, that is the actual cost. And what is the amortized cost for that? So this is where we are going to require a very sophisticated and a good mathematics. Okay. Notice that if the actual cost is Ci, for any potential function you can define Ai like this mathematically, then sigma Ai is greater than or equal to sigma Ci. Our goal is to prove that this is n log n, so that n log n is the bound for the actual cost. The actual cost is a very fluctuating and varying one. It depends on the height, it depends on from where you have triggered the splay, because it has to go all the way up by rotation. Each rotation will promote one level or two level, but that requires two rotations. But so whatever is the number of operations that you have to do, the number of rotations you have to do is very large. It depends on the depth. Right? Therefore, the actual cost is proportional to the depth, but the tree becomes shorter after a splay operation, which is making the subsequent operations cheaper. That is why this is also called self-adjusting trees. The tree reconfigures itself with every splay operation, so that the operations done subsequently are all cheaper. Okay. So it's a beautiful data structure and concept. So let us see how. So we have to come up with a potential function. Potential function. This potential function is going to be really strange. Okay. So let us consider Si is the size of the tree rooted at okay, we are using x. Let S x with the size of the tree rooted at x, size of the subtree rooted at x, and R x equal to log S of x, log S of x. Okay. And phi of a data structure is sigma Rx, x belongs to the set. For every x there will be a node, that node is in some tree, and that it will be, there will be a subtree rooted at that node that will have certain number of nodes, that is S of x, and R of x is log of that. Add this log of these ones, you are going to get the potential function for that. So the potential will change after a Splay operation, because the tree is completely the shape has changed. Okay. So for example, let us take the following example: 5, 4, 3, 2, 1. Okay. Let us consider this tree. The size of the subtree at 5 is, therefore this S of 5 will be 4, S of 4 will be, oh sorry, 5, I am sorry, all the nodes 5 will be 4, S of 3 will be 3, S of 2 is 2, S of 1 is 1, therefore R of 5 is log 5 to the base 2, this will be log 4, log 3, log 2 and log 1. Okay? This is the sum. Therefore, what is the potential of this tree? Potential of this tree, phi of this tree is sigma log I going from 1 to 5. This is the potential. Suppose I splay 1. So when you splay 1, what happens? 1 goes to the place of 3. So 1 goes to the place of 3, 2, 3. So to the left of 4 you will have 1, to the left of 5 you will have 4. So 1 goes 2 level up, it is taking the place of 3. So the first step is this, you have to recursively proceed, again you have to splay. So when you take splay, okay, the 1 goes to the top, 1 it goes to top, 4 becomes the right child, 5 becomes the right child, the right child becomes the left child, 2, 3. Splay 1 will transform this tree to this. Now what is the potential of this structure? The potential of this structure is this, you can see one has got all the nodes, so that will be log 5, and 4 has got all the 4 element log 4, log 5 this is 0 because this is only one element, this is also 0, and then plus log 2. Log this is 0 and that is 0, there is only one node. Log 1 is 0, size will be 1, the size will be 5, the size will be 4, the size will be 1, 2, 1. So log of these 3 numbers, all the 5 numbers, log of this becomes 0. So you can see that the potential is changed. That is log 5 plus log 4 plus log 3 plus log 2 plus log 1, only log 1 is 0. So there is a reduction in potential. This has a smaller potential. Okay, it is smaller by log 3, that much is reduced. So potential changes. Potential before, potential after. The Splay operation. Okay, so this is the potential before and potential after. So what is the amortized cost? Amortized cost AI is actual cost plus potential difference. Okay, potential after minus potential before. Okay. So now let us see how the potential changes. We are going to take one particular case and then we are going to show how the potential changes. The same kind of changes, it will keep accumulating as we go along, right, because each change is causing certain change in the potential, and we will calculate the total change in the potential, then add with the actual cost. All right. So let us consider the actual cost of, let us consider the amortized cost of search. For everything it is, the logic will be the same. Okay, what is amortized cost of? So let us assume that the item is in the set. So you would have taken the tree starting from the root, you would have gone to the left, right and other things, and you would have come here and then reported that X is in the set. If it is not there, you will come to a leaf and then say that it is not there, and you are going to start the Splay from that node where it has failed. If it is there, you are going to start the Splay from there. So the cost, you come down, keep coming down, and then you start the Splay operation. So let us look into the Splay operation. What is the actual cost in Splay, and what is the potential difference created by the Splay? So let us consider X, parent Y, parent Z, A, B, C, D. The Splay operation has turned this into X, Y, Z, A, B, C and D. Okay. Now we are going to call the potential after this tree. So if you look into the ranks, it is the sum of the ranks. So potential after minus potential before will have lot of terms cancelled out. The ranks of the vertices, the nodes in A, B, C, D is not altered, because the size of the subtree there remains the same. The sizes of the subtree under X, under Y, under Z changes. Only their ranks change. All other nodes and their ranks do not change. Therefore, potential after, you call this as T dash, you call this as T, minus potential before will have only rank of X in T dash, rank of Y in T dash, rank of Z in T dash, minus rank of X in T, rank of Y in T, rank of Z in T. All other ranks are cancelled. Okay? Because what is the definition of phi of a tree? Phi of a tree, sum of the ranks of the node X belongs to the vertex set of T. All the ranks here remain same. So when you subtract in this expression, they get cancelled. Let us denote rank of X in T dash as R dash X, rank of Y in T dash as R dash Y, rank of Z in T dash as R dash Z. Similarly, rank of X in T, you call it as R of X, rank of Y in T, you call it as R of Y, rank of Z in T, R of Z. Then phi of T dash minus phi of T, the potential difference is equal to R dash of X plus R dash of Y plus R dash of Z minus R of X minus R of Y minus R of Z. Right? This is the potential is given by this sum. When you consider the potential difference, the nodes which do not change its position, their rank will be same, they will cancel out. Only X, Y and Z have changed their positions. So that subtrees under them might have become smaller or larger, their ranks are different. Therefore, only these ranks will survive in the difference. All others get cancelled. So, phi of T dash is okay. The first thing that you observe is these two gets cancelled. Why? Look at the tree. Okay. So under Z, you had earlier rank of Z. What is rank of Z? How many nodes are there? Whatever you have in A, B, C, D. So A plus B plus C plus D. X, Y, Z. So rank of Z, R of Z is log of A plus B plus C plus D plus 3. Because whatever is the number of nodes in A, number of nodes in B, number of nodes in C, number of nodes in D, plus the node X, Y, Z. That is the total. This is R of Z. Now what is R dash of X? Whatever is in A, B, C, D plus 3. This is also log of A plus B plus C plus D plus 3. That is the reason why r dash of x is same as r of z. That is why I have cancelled it here. R dash of x and r of z are same. Okay. Now we have to eliminate. We want to see, you are recursively continuing at the new position of x, at the new position of x. So I would like to have only rx and r dash x. All other things I have to eliminate. So here I have r dash y, r dash z, r of y. There are several entries are here. So we have to eliminate them. So how do we eliminate them? So the first thing that you observe is r of y is greater than or equal to r of x. R of y is here, that has got lot of nodes under it. This is x. In fact, every node under x is under y also, and y may have some more nodes under it. Therefore, r of y is greater than or equal to r of x. So this r of y I am going to replace by r of x. So I am subtracting a smaller number. R of y is bigger. When I subtract a smaller number, the expression becomes, it is less than or equal to r dash y plus r dash z minus r of x minus r of x. This is because r of y is greater than or equal to r of x. That is the reason why replacing with a smaller number makes the right hand side larger. Earlier a bigger number was subtracted, now a smaller number is subtracted, therefore the value of the expression becomes larger. Okay. So I have eliminated r of y. Now we have r dash y, r dash z, all these things are here. So r dash y, r dash z are here. Now r dash y is less than r dash z, therefore less than or equal to r dash x plus r dash z minus 2 rx. So I have removed r dash y also. This is because r dash y is less than or equal to r dash x. Why this is so? X has become the grandparent, y has become its child. So y and its subtree are below in T dash. Okay. So here you can see y r dash y, this is defining r dash y, the whole thing is defining r dash x. So r dash x will be larger. Okay. So I have replaced this. So I have eliminated y from the scene. Okay. R of y is eliminated, r dash of y is also eliminated. R dash of y is eliminated using r dash of x, r of y is eliminated using r of x, r of y is eliminated using r of x. Now we have r dash of z is still there, and we need to eliminate that, right, because we want only a relation that is connecting r dash of x and r of x, because you recursively continue at the new position namely in t dash you continue at x. That is the reason why my goal is now to eliminate r dash of z. So how do I eliminate r dash of z? Now we look into the following facts and use that to eliminate r dash of z. Okay. So we will look into the details of eliminating r dash of z in our next session. Thank you.